Hello everyone, I'm Alka Jangid from IIT Kanpur. I'm your TA for Nature and Properties of Materials. And today's lecture is Smart Materials, and this course is offered by Professor Bishop Bhattacharya, Department of Mechanical Engineering, IIT Kanpur. Firstly, we'll be going through some sample assignment questions. So, first question is, in case of direct piezoelectric effect, the tensile stress along the polarization direction generates. Your options are voltage of the same polarity as the Pauling voltage, or voltage of the opposite polarity to that of Pauling voltage, or it does not have any effect, or it leads to short circuit. Your answer will be voltage of the opposite polarity to that of Pauling voltage. Now this can be explained. In case of direct piezoelectric effect, tensile stress along the polarization direction generates a voltage of the opposite polarity as the Pauling voltage. It can also be tensile stress along the polarization direction generates a voltage of the same polarity as the Pauling voltage. So these both statements are correct for direct piezoelectric effect. Now next question is, which piezoelectric polymer out of the following shows the largest piezo effect? Your options are PVDF all cis, PVDF trans cis, PVDF all trans, or PVC. Your answer will be C. So this is what PVC looks like, PVDF. So it is its monomer is vinylidene difluoride. So in case of its full form is polyvinylidene fluoride or polyvinylidene difluoride. It is a highly non-reactive thermoplastic fluoropolymer produced by the polymerization of vinylidene difluoride. Its chemical formula is C2H2F2. This is a monomer unit times the N. So PVF2 is polyvinylidene fluoride, a semi-crystalline polymer consisting of long chain molecules with the repeat unit of CF2CH2. Now form 1 PVDF, which is all trans, it shows all chains oriented parallel to the axis of the unit cell and the dipoles pointing in the same direction. Third question is, a helical magnetic field producing torque in magnetostrictive material is known as. Your options are magneto-volume effect, Villari effect, Matteucci effect, or Widman effect. Answer will be D, Widman effect. Now it can be explained by saying that when magnetic field is converted into torque, it is represented as a reverse magnetostrictive effect known as Widman effect. When stress is converted into change in magnetization, it is represented as direct magnetostrictive effect known as Villari effect. When torque is converted into EMF induced, it is represented as direct magnetostrictive effect known as the Matteucci effect. And magnetic field, when it is converted into change in volume, it is represented as reverse magnetostrictive effect known as magneto-volume effect. Now fourth question is, find the odd material out. First option is piezoelectric lead zirconate titanate. Second option is magnetostrictive terphenol T. Third option is phase dependent shape memory alloy. Fourth option is hydrogen PHEMA. Answer is hydrogel. Now we can explain this by saying that hydrogel PHEMA is poly 2-hydroxyethylene methacrylate. Now it is a polymer that forms a hydrogel in water, and it is a biocompatible, optically transparent, hydrophilic and non-degradable polymer. And other materials here remaining, they are all smart materials which change their properties based on stimuli. So these all can be used in making actuators and sensors, while this can be used. Properties of other materials, PZT, PVDF, terphenol T and nitinol, these all are given here. So based on change in stimuli, these are the strains that we see in these materials. And this is the structure of your hydrogel. Now question 5. Among the following, which one cannot be used as an actuator? Your options are shape memory alloy, second is optical fiber, third is magnetostrictive materials, or electromagnetorheological fluids. Answer will be optical fiber. In case of optical fibers, it is used for transmitting optical signals, and these are passive smart materials which lack the inherent capacity to transduce energy. That's why they can act as only sensors but not as actuators. And other materials in options are smart materials, these SMAs, magnetostrictive material and electromagnetorheological fluids. So these which can change properties that can be significantly changed in a controlled fashion by external stimuli. And these materials, in case of shape memory alloy, they convert temperature change, it leads to shape change. In magnetostrictive materials, magnetic signals they change in strain. And in case of electromagnetorheological fluids, change in electric or magnetic field leads to change in viscosity of a fluid. Now question number 6. In case of converse piezoelectric effect, voltage of same polarity as the Pauling voltage causes, the options are extension along the Pauling direction and contraction perpendicular to the Pauling direction. Second option is extension along and perpendicular to Pauling direction. Third option is contraction along the Pauling direction and extension perpendicular to the Pauling direction. Fourth option is contraction along and perpendicular to the Pauling direction. Answer will be A. Now in case of converse piezoelectric effect, the statement goes as voltage of the same polarity as the Pauling voltage causes an extension along the Pauling direction of the and contraction perpendicular to the Pauling direction. It can also be if voltage is of opposite polarity, then there will be compression along the direction and contraction and extension in perpendicular direction. And this is what it will look like. For the question number 7, a piezoelectric sheet of length 0.0508 meter, width is 0.0245254 meter and thickness 0.000254 meter as shown in figure. Here the sheet is subjected to a force along the one direction. So this one direction is this one, and the voltage V 100 volt is applied to the electrodes. Now these electrodes are applying 100 volts. Now the required constant values are as follows. So D31 is given, S11E is given. So now we have to calculate the free strain of the sheet in microstrain. Your answer will be this. Now this can be calculated by using this simple formula. D is a constant, so here Ik equals to strain induced in I direction. I will be 3, so we know that strain will be in 3 direction because we are applying voltage also in this direction, and electric field applied in K direction. K is here 1, in one direction we are applying electric field. Now strain induced D will be, if we want to calculate this part, so we'll be multiplying both of these. So D31 multiplied by electric field applied. Now strain induced can be calculated by simply D31 is minus 274 multiplied by 10 to the power minus 12 meter per volt times the electric field applied. Now electric field can be given as voltage divided by length. Length will be, we are applying in this direction, so length will be thickness, and thickness is given in meter, so we can also write this in 254 times the 10 to the power minus 6. So your answer will be minus 107.87 times the 10 to the power minus 6. Now they have asked in microstrain, so micron part you can remove 10 to the power minus 6, so this will be answer minus 107.87. Question number 8. Now which combination is correct? So first option is that thermochromic materials, they convert temperature into color change, and shape memory alloys, they convert temperature into deformation, or magnetostrictive materials, they convert magnetic field into viscosity change, or thermoelectric materials, they convert temperature into potential difference. So your answer will be C. Now in case of magnetostrictive materials, magnetic field is converted into deformation, while when magnetic field is converted into viscosity change, it is called a magnetorheological fluids. Now question number 9. Which one of the following is not a shape memory alloy? Your options are nitinol, aluminium, copper zinc aluminium, or copper aluminium nickel alloy. Now answer will be aluminium, because all others are alloys which show shape memory effect. A shape memory alloy is an alloy that can be deformed when cold, but it returns to its pre-deformed or remembered shape when it is heated. A mix of roughly 50% nickel and 50% titanium is the most common shape memory alloy, and it is known as nitinol. And in case of copper zinc aluminium and copper aluminium nickel, they are also widely used. Now the question number 10. A piezo stack has 1000 layers, and it has the following electromechanical coupling coefficients: D31 equal to 10 to the power minus 12 meter per volt, and D33 is equal to 10 multiplied by 10 to the power minus 12 meter per volt. If the stack is subjected to 1 kilovolt of voltage across the stack, and if the stack is 10 centimeter in length, the change in length will be, options are 100 micron meter, 1 micron meter, 10 micron meter, or 1 meter. Your answer will be 10 micron meter. Now the simple formula that is used is delta L equals to N times the T33 times voltage. Delta L is change in length, N is number of piezo layers which is given, and length we have to calculate. T33 is longitudinal piezoelectric coefficient which is given, D33 is also given, and V voltage is 1 kilovolt. So operating voltage, so we can put values of all these three and we can obtain delta L. So N is 1000, D33 is 10 times 10 to the power minus 12, and V is 1000 voltage. So answer will be 10 times 10 to the power minus 6 meter or 10 micron meter. Now we'll be going through some lecture slides. So firstly, smart materials. Smart materials are also called intelligent or responsive materials, which are designed materials that have one or more properties that can be significantly changed in a controlled fashion by external stimuli such as stress, moisture, electric field, magnetic field, light, temperature, pH, or chemical compounds, etc. Features of smart materials. Now these materials are a part of, one second. These materials are part of a group of materials broadly known as functional materials. So it is a subcategory of functional materials, and the basic energy forms that get interchanged are thermal energy, electric energy, magnetic energy, sound energy, and mechanical energy. Analogous to biological materials, so such as biomaterials, they are adaptive. These all properties which biomaterials show, and smart materials also show these properties, which is adaptivity, cellular function, self-sensing, actuation, and control. And smart sensors and actuators are highly embeddable. Now, smartness is a scale of intelligence. Now, if we choose a scale where stupid, dumb, foolish, trivial, sensible, smart, intelligent, wise, this is a scale, then currently in present time, smart materials are in the range of highly sensible to the poorly intelligent. In this area, we are working with our materials. And passive smartness to active smartness. So there are two types of smartness, which can be passive or also active. In case of passive smartness, there will be some lack of inherent capacity to transduce energy, and they can act as only sensors but not as actuators. Example is optical fiber cable and multi-phase rocket nozzle of space shuttle, or porous tungsten with silver coating, graphite, ceramic layer, and steel. These all are passive smart materials. Now, traditional versus smart systems. So in case of traditional systems that we use, they are designed for certain performance requirements. Example, for bearing some load, or for some speed or certain lifespan, and these are unable to modify its specifications if there is a change in environment. While in case of smart systems, they can accommodate unpredictable environments, they can meet exacting performance requirement, and they offer more efficient solutions for a wide range of applications. In case of direct effect, all piezoelectric materials and PVDF, Magnetostrictive materials, optical fibers, these all show direct effect. And what is direct effect? In this case, our stress will be converted into some electric, magnetic, uh, these type of signals. So it is known as direct effect, and these materials can be used in making sensors. In case of converse or reverse effect, what will happen? There will be electric, magnetic, thermal stimulus. These can be converted into strain. So these materials show reverse effect, and these can be used in making actuators. Now these are certain examples. In case of ferroelectrics, perovskites, piezoceramics, PVDF, they respond to electric field by change in shape. And terphenol D amorphous matte glasses, they show a similar effect with the change in magnetic field. Shape memory alloy respond in a similar manner but with the change in thermal field. And electromagnetorheological fluids, they respond to electric magnetic field by changing its viscosity. Now why smart sensors and actuators? Because smart materials can be used in making smart sensors and actuators because they show real-time response and they exploit functional properties, and they also have better embeddability and show minimal effect on structural properties, and there will be reduction in weight if compared to like if we use some mechanical machinery which is made for performing the same task as the smart material, then there will be reduction in weight if we use smart material, and there will be less power consumption compared to mechanical machinery, and there will be better reliability. Now, smart materials in nature. So one of the example is pine cone in water. So when a pine cone, which is shown here, when it is submerged in water, it starts changing its shape and it retracts itself. So as best weather for planting pine trees is when it is warm and dry. So when it's cold and wet, pine seeds can disperse in wind, and because of a hygroscopic material below this underneath pine spikes, a smart material that absorbs moisture and expands. So because of expansion of that particular part, it starts to retract itself, and these seeds, they won't come out in water. In case of history, smart materials in history, we see that pyramids of Giza, they are made of using a self-healing material which is known as lime mortar, which is concrete like material, and it is used to construct these. It heals itself when a crack develops because by a reaction with the moisture and carbon dioxide present in the air and forms limestone, and that limestone grows into a crack to completely heal the material. Now, first time smart materials came to notice when piezoelectric effect was discovered in 1880 by two French physicists, which are brothers Pierre and Paul Jacques Curie, and in crystals of quartz, tourmaline, and Rochelle salt, which is also known as potassium sodium tartrate, and they took the name from the Greek word paisin, and which means to press. So because of pressing there will be some electricity generated, so these materials are called piezoelectric materials. Now there are various categories of smart materials, and these are the input and the the conversion. After conversion, what output is there, these are given. In case of piezoelectric material, it will convert some deformation into potential difference. And in case of thermochromic materials, if there will be change in temperature, it can change color. In case of photochromic materials, photo will be some radiation, so it will change color. In case of shape memory alloys, if there will be temperature change, they can show deformation. In case of electrostructive material, potential difference leads to output of deformation. In case of magnetostructive material, magnetic field, it shows output deformation. In case of thermoelectric material, temperature will change into potential difference. Now some types of smart materials. Now these are the smart materials that will be part of course. So first is piezoelectric material, second is magnetostructive material, smart polymers, shape memory alloys, thermochromic materials, and photochromic materials. We'll be studying about all these. In case of piezoelectric material, stress can be converted into electric charge, or electric field can be converted into mechanical strain. In case of shape memory alloy, heat is getting converted into original memorized shape. In case of electrorheological fluid, electric field will be converted into change in viscosity or internal damping. Magnetostructive material will be magnetic field will be get converted into mechanical strain. Now first material that we'll be studying about is piezoelectric material. Piezoelectricity. Electricity from pressure was discovered by Pierre and Jacques Curie in 1880. And piezoelectric material convert electrical energy to mechanical energy and vice versa. They can be used as actuators, as they provide a voltage to create motion. Sensors such as many accelerometers, energy harvesters, since the charge generated from motion can be harvested and stored. The applications of piezoelectric materials are in making BBQ igniters and actuators for inkjet printer heads, energy harvesters, sonar equipment, ultrasonic cleaning, and flow control devices. Now this is a piezoelectric effect in quartz. In quartz, what will have silicon atom and oxygen atom. So it will have positive charge, it will have negative charge. If you are no stress, in that case there won't be any charge distribution. But if we are applying tension on this material, then this side will be having dominantly positive charges and this side will have dominantly negative charges. If we are applying compression, then this side will be having negative charge, this side will be having positive charge. Now there are two types of piezoelectric effects. First is direct, second is converse. In case of direct, your stress will be converted into voltage. In case of converse, voltage will be converted into some strain. Now in case of direct, compressive stress, compressive / tensile stress along the polarization direction generates a voltage of the same / opposite polarity as the Pauling voltage. In case of converse, voltage of the same polarity as the Pauling voltage causes an extension along the Pauling direction and contraction perpendicular to the Pauling direction. If we are using voltage of opposite polarity, then there will be compression along the direction and extension in perpendicular direction. In piezoelectric materials, these are the equations of piezoelectricity. For direct effect, D will be equal to dx plus epsilon E, and in converse effect, X will be Sx plus dE. Here the symbols are: capital X is stress, small x is strain, capital D is electric displacement or flux density, S is compliance, E is electric field intensity, small e is permittivity, and D is piezoelectric constant. Now, as already told, in direct effect, stress will be converted into electric potential. In converse effect, electric signal will be converted into strain. So, we are measuring strain in converse effect. And D is electric displacement that will be calculating. In case of magnetostrictive materials, in 1842, James Prescott Joule noted that a ferromagnetic sample changed its length with the application of magnetism. Now, magnetorestriction E in materials due to domain migration and reorientation under applied magnetic field H. So, if a crystal of ferromagnetic material is initially in a compressed state, the effect of magnetostriction becomes more pronounced, and all ferromagnetic elements show magnetostriction to different degrees. It is observed that the maximum one can achieve is for cobalt, which saturates around 150 microstrain, which is ppm. Now, this is what magnetostrictive effect will look like. So, in absence of magnetic field, these domains are oriented in random orientations. So, this, if we are applying magnetic field, they are all oriented in same direction. So, there will be some extension in material. In case of in general, large force, deflection and energy conversion efficiency, these are, and they do not decay with time. And magnetostrictive transducers, they are cost effective in low frequency band and could be effectively used for deep sea measurements due to superior mechanical properties. Now, similar to direct and converse effect, here it is Joule effect and Villard effect, and the equations are as following. Here epsilon equal to SH sigma plus DH and B equal to D sigma plus mu sigma H. Now, here B is magnetic flux density, H is magnetic field intensity, D is magnetostrictive constant, SH is compliance matrix of the material at a constant magnetic field, and mu is permeability of material at constant stress. Now, these are various materials and their magnetostriction. So, this is what their expansion will look like. In case of nickel, there will be contraction, and these are the Curie temperatures. Now, highest magnetostriction in ppm is for this TB Fe2, this phase, and in this TB 0.3 dy 0.7 Fe 1.9, this alloy. magnetostrictive materials. Now these effects of two types, direct and reverse. In case of direct, stress can be converted into change in magnetization, or torque can be converted into EMF induced. Change in volume can lead to change in magnetic state, or in case of reverse, magnetic field can be converted into dimension change. Magnetic field can be converted into torque. Magnetic field can be converted into change in volume. Next is smart polymers. Polymers that respond to external stimuli by changing shape or size are known as active smart polymers. Now these are of two types, active polymers and electroactive polymers. Active polymers, these respond to input stimuli such as pH, magnetic field and light. Example is polyanionic cellulose. And electroactive polymers, these respond to change of electrical input, also known as EAP. Now electroactive polymers, they respond to electric stimulus, are broadly classified into two groups. These are electronic EAP and ionic EAP. Electronic EAP is driven by electric field or Coulomb forces, and ionic EAP is changes shape by mobility or diffusion of ions. Smart polymers. Now the electronic EAP and ionic EAP, they are different, and the differences are that in case of electronic EAP, they need high activation voltage greater than 150, and ionic, they require low driving voltage from 1 to 5 volt. In electronic one, they have high energy density and rapid response time, which is in milliseconds, while ionic, they are relatively slow response time, but the amount of deformation is more, and they perform better under wet conditions. Examples of EAP are dielectric EAP, electrostrictive paper, ferroelectric polymers, and liquid crystal elastomers. In case of ionic polymer gels, ionic polymer metal composites, conducting polymers, and carbon nanotubes. Shape memory alloys. Now a shape memory alloy is an alloy that can be deformed when cold, but it returns to its pre-deformed remembered shape when heated, and it may also be called memory metal, memory alloy, smart metal, smart alloy, or muscle wire. So here we have dropped this wire by deforming, then it regains its original shape when it is dropped into hot water. A mix of roughly 50% nickel and 50% titanium is the most common shape memory alloy, which is known as nitinol, which was originally developed by the Naval Ordnance Laboratory. Copper, zinc, aluminium, and copper, aluminium, nickel are also widely used. The principle of shape memory alloys is they have ability to remember its austenite phase. As the metal is cooled to the martensite phase, it can be easily deformed. When the temperature is raised to the austenite phase, it reforms to the original shape of the material. Pseudoelasticity is when the metal is changed to the martensite phase simply by strain. The metal becomes pliable and can withstand strains up to 8%. In case of advanced materials, they still under development include magnetically activated shape memory alloys. Now this is how we can convert detwinned martensite by heating into austenite, and then upon cooling it again gets twinned and then on loading it can get detwinned. On unloading it again becomes in its original shape. Shape memory effect. Now certain classes of metallic alloys have a special ability to memorize their shape at a high temperature and recover large deformation imparted at a low temperature on thermal activation. And the recovery of strains imparted to the material at a lower temperature due to heating is called the shape memory effect. Shape memory effect was first observed in 1932 in gold cadmium alloy. Now, three types of shape memory alloys are currently popular: copper, zinc, aluminium, copper, aluminium, nickel, and nithinol, which was discovered in 1962. And the last one is commercially available as nithinol, and NOL stands for Naval Ordnance Laboratory in USA. Manufacturing of shape memory alloys are typically made by casting using vacuum arc melting or induction melting. These are specialized techniques used to keep impurities in the alloy to a minimum and ensure the metals are well mixed. The ingot is then hot rolled into longer sections and then drawn to turn it into wire. Applications of smart shape memory alloys. So in one way shape memory effect, the material remembers only the high temperature shape. In two-way shape memory effect, the material remembers both a high and a low temperature shape. So applications are in control of aerodynamic surfaces, microcoils for vibration isolation, grasping by robotic fingers, space exploration, which is for rock splitting, nitinol filter, and deployment of solar array hinges. In case of two-way uh, shape memory effect, firstly we are using this original shape which is below martensitic temperature. So we are plastically deforming it below this temperature. Then on heating it will obtain the shape of high temperature, and then again on cooling we can get the shape which was given it at lower temperature. So it can remember both the shapes. Thermochromic materials. Now thermochromic materials, they change color reversibly with changes in temperature. They can be made from semiconductor compounds, liquid crystals, or metal compounds. And the change in color, it happens at a determined temperature which can be varied by doping the material. Applications include, they are used to make paints, inks, or are mixed to molding or casting materials to for different applications. Now this is what liquid crystal looks like. So firstly when it is closer together it is giving blue reflected light when it is hot, and when it is gets cooled so the distance between them increases and this reflected light is red. Photochromic, as the name suggests, photo will be light, so light or some radiation. So photochromic material change reversibly color with change in light intensity. Usually they are colorless in a dark place, and when sunlight or ultraviolet radiation is applied, a molecular structure of the material changes and it exhibits color when the relevant light source is removed and the color disappears. Application is in making sunglasses, data storage, novelty items, smart windows, solar energy storage, etc. Now this is how chemical structure changes for transazobenzene. When we apply light, so it will change into cis-azobenzene. So these both will be having different colors. And for making glasses also, if we are going from dark place to a place with high sunlight, so this glass will change its color and it will protect our eyes from sunlight. Applications of shape memory alloys. So they are used in making aircraft and spacecrafts and dental braces, high strain energy absorbing applications, reducing vibrations in helicopter blades, fire security and protection systems, because they are very sensitive towards temperature, and they can be used in making eyeglass frames, in anti-scalding devices or fire sprinklers, household appliances. They can prevent structural damage to bridges and buildings, and in case of robots also, their arms and all, they, if we want to make them sensitive to temperature, we can use shape memory alloys. Now biological applications in making bond plates, surgical anchor, clot filter, catheters, retainers, these also can be used using these. Now problem with shape memory alloys. Now they show fatigue from cycling, so they can cause deformation and grain boundaries, and they begin to slip along planes and boundaries. And if we overstress, a load above 8% strain could cause the shape memory alloy to completely lose its original austenite shape. And difficulty with computer programming, and they show they are more expensive to manufacture than steel and aluminium, which are not smart shape memory alloys, and they are relatively new. Potential applications of smart materials. Now smart materials, they can be used in making self-healing asphalt. So if we are making roads using this, so if a road gets damaged from some place, so it can self-heal itself. So it will increase the lifetime of the road. And self-healing concrete. So concrete which we use for making buildings also can self-heal itself, and it will, if it gets damaged and some cracks appear, so they can get themselves healed. Self-healing coatings, so various coatings also are made using these. Orthopedic surgery, in making smart aircrafts, and in smart fabrics, in making intelligent glass. So glasses we also saw, and so in case of robotics also we use shape memory alloys. Smart skin for submarine, and smart bridges. In case of bridges also, it is as shown here. So we can use piezoelectric materials on the road. So if a vehicle is passing through there, so we can store a lot of energy, we can convert it into electrical energy, and we can use self-healing asphalt also for making these roads, and some other materials also can be used. Now merits of using smart materials. So these have good mechanical properties, and they are biocompatible, and they have simplified packaging, and they have compactness compared to mechanical machinery, as I told before, and they have safety mechanisms. So with temperature or with radiation, they are sensitive to them, so they can provide some safety mechanism to some electrical circuits, or or to buildings also, in case of self-healing healing mechanism. high energy density, durability and reliability. They are excellent bandwidth and they can be self-repaired. And demerits of smart materials is that they are more expensive, they are not easily available in market, and they have low energy efficiency. And some smart materials may have low energy efficiency and they have complex control also, and they are highly sensible, so they require more care while storage. And environmental pollution can also be there, like if some material is toxic in nature, so we can't dispose it easily, and long term effects are unknown. These are the some applications of smart materials. So actuators, they are mainly used in making actuators, then making sensors, transducers, and these are structural materials, and some other applications such as in making robots and all. Conclusions. Now we can conclude by saying that in certain respects, smart materials are an answer to many contemporary problems, and as resources are diminishing, they promise increased sustainability of goods through improved efficiency and preventive maintenance. In medical applications, they offer early detection, automated diagnosis, and even self repair. And in case of artificial intelligence field, they may offer sophisticated biowarfare countermeasures or provide targeted scanning and intelligence gathering in particularly sensitive environments. Now these are the references. So Wikipedia, NPTEL, and all these websites, these are used for making slides. And that's all from my side. I'll be repeating questions once again. So first question is based on direct piezoelectric effect. So there are clear statements that you can remember. So for direct piezoelectric effect, what will happen? So voltage is converted into, so your stress that you will be applying, that will be converted into voltage, and in converse it will be opposite. Second question is which piezoelectric polymer out of following shows the largest piezo effect? So we saw that in PVDF all trans it will be showing largest piezo effect. A helical magnetic field producing torque in magnetostrictive material is known as, answer will be Whitman effect. Field of odd material, find the odd material out. So hydrogel, it can't be used, it is a passive smart material. So others are like they can be used in making actuators and sensors. So this is odd material out. Fifth question is among the following, which one cannot be used as an actuator? So your answer will be optical fiber, because it is a passive smart material. So it can't be used in making actuators, it can only be used in making sensor. In case of converse piezoelectric effect, so as I told earlier, voltage of same polarity as the Pauling voltage causes extension along the Pauling direction and contraction perpendicular to Pauling direction. Seventh question was numerical and it has simple formula. So this constant will be equal to strain induced divided by electric field applied. So just find out electric field. You have to divide this voltage by thickness. and then you can multiply it with D31. Which combination is correct? So only one is wrong, which is magnetic field is converted into deformation, then it is magnetostrictive. If it is viscosity, then it will be magnetorheological material. Ninth is, which of the following is not a shape memory alloy? So aluminium is the answer, others are shape memory alloys. Another numerical, so in this there was simple formula, delta L is equal to N times D33 times the voltage. So all things are already given, you just have to put values and answer will be 10 micron. This is what we talked about. Firstly, what are smart materials, features of smart materials, scale of smartness, traditionally smart systems, direct effect, converse or reverse effect, why smart and actuators, smart materials in nature, smart materials in history, then when the first smart material was discovered. These are the various classes of smart materials. Firstly, we talked about piezoelectric material, two types of effects, direct and converse effects, their equations, then magnetostrictive materials. There are also two types of effects and their equations. Then smart polymers. There are also of two types, active polymers and electroactive polymers. Electroactive was further divided in two parts, electronic and ionic. Then their differences. Then we talked about shape memory alloys, principle of shape memory alloy, shape memory effect, their examples, how they are manufactured, and what are their applications. There are two types, one-way effect and two-way effect. Then we talked about thermochromic materials, photochromic materials, applications of shape memory alloys, problems with shape memory alloys, potential applications of smart materials, then merits and demerits of smart materials, then we concluded, and references. So that's all from my side.